All right, welcome to part 2 of your texting and driving coding program, where we're going to talk about the distance traveled while braking, and then we're going to do total distance the car travels, distance the walker, and finish it off with a true-false statement saying whether or not your pedestrian survived. Okay, so just like in the previous part, we got to start by getting organized. So we've got all of our inputs organized on the left side, and then our calculations organized on the right, and then we're going to make use of this middle column as well for a needed calculation. So let's get started. Well, what do we need to do to calculate the distance traveled while braking? Well, here's all of the inputs that are required for us. These are found on your system analysis summary calculations that you did by hand. Okay, so these ones you did by hand, these 4-step method problems. We're going to do number 3, number 4, number 5, and number 6. Okay, we're going to have our computer do all those, 3 through 6. Okay, cool. Now, let's set up what we need. Well, we need to know first the velocity of the car before braking. This is the initial velocity, v initial. And just like before, I'm going to have these justify over to the right-hand side so it looks a little better. There we go. And then this is the velocity of the car after braking. And remember, we called that in our physics terms, we used the phrase v final. Okay? That's what it's going to look like in our equation. All right. What else do we need to know? Well, we need to know the deceleration of braking. How strong are our brakes? And we also need to know the time of braking. How long does it take to come to a stop? And then I'm actually going to insert some rows here, so I have a little bit more space. Insert one row above, so give me another row there. And that's where I'm going to put the distance traveled while braking. Okay, lots of stuff to record here. Let's continue getting organized by putting our units in. So I've got a velocity here, that's meters per second. And then I got a velocity here, that's meters per second also. The deceleration of braking is an acceleration, so I've got meters per second per second. The time is going to show up in this column here. So I'm going to put seconds in the column to the right of it. And then finally, we're going to have distance traveled while braking. That's going to be in meters. Okay, now let's color code our cells. So just as before, anything that we're calculating, we don't want the person to touch, so it's going to be in red. And then this is a needed calculation. I'm going to also have that as a slightly different color. That's going to be in yellow. And then over here, we've got our inputs. These are things that we can mess with. We can change them. We can experiment around with them. So I'm going to put these in as green. And then for our scenario, we know that the velocity of the car before braking, the v initial, is just the same as the velocity that we had before we started the braking procedure. So I'm going to hit equal sign and make it equal to whatever I've got right here. So I'm just going to click in that cell. There's C13. Okay, so C21 is equal to C13. It just automatically plops in my 10 meters per second there. And we know also, because we're trying to come to a stop, our velocity of the car after braking, our v final, should be 0. We're trying to stop. Okay, and a good placeholder value that we had on our system analysis summary calculations for the deceleration of braking was -8 meters per second. This is a pretty average value for most braking systems. So it's -8 meters per second. Great. Now, we're going to do some coding with these values. So we need to take a look at our equations that we used for problems number 3. So the equation we used for calculating the time, and the equation we used for number 4. Okay, good thing. I've got the equations right here. Okay, so here's what our formula looks like. For the braking time, it looks like this. The t braking is equal to v after, so the final velocity, minus v before, so the initial velocity, all divided by the acceleration of braking. And notice how we've got it in a big parentheses there. That's going to help us keep everything straight. So to start coding, I'm going to hit equal sign, and I'm going to do big parentheses to put things in top. And notice how I have a frowny face here. Okay, frowny face. That frown is going to be turned upside down. All right, so we've got the final velocity minus the initial velocity and then I'm going to close the parentheses. Okay, double check that I've got that in the right order. The final velocity, v after, is first, and then the v before is afterwards. Okay, so I've got v after minus v before in parentheses. Great. Now I want to divide. How do I divide? I do a slash. Okay, so a slash here next to your right shift key, slash, and then I've got my acceleration here. So my acceleration is just this value right there, and then I'm going to close parentheses. And notice how I've got different colors for each one. So my orange is there, my purple is there, and my blue is there. Okay, that's going to help us get all of these variables sorted out. Now, if we hit equal sign, we should get, oh no, we didn't get 1.25. Remember, 1.25 was the value we expected to see. Here, from this calculation, we got 1.25. That is the correct answer, but why isn't it popping up? Well, the reason is we're doing some rounding here, okay? So it's rounding 1.25 to 1. So how do we make it not round? I don't want it to round. Okay, up here, there's a little button called Increase Decimal Places. So I'm going to click that, and it gives me that. When I click it twice, it gives me 2 extra decimal places. So there it is. So let's show that again. I can decrease the decimal places back down to 1. Up here, I can increase them to as many as I want. So I can give it like all these decimal places. Don't do that. It's annoying. Okay, just give us 2 decimal places. Thank you. Okay, cool. We've got our value for the time of braking, and this was one of the inputs for the distance traveled while braking. That's why we had that calculation, okay? Because we had to take an answer from number 3, and we had to plug it in, use the result from calculation 3, we had to plug it in down here. All right, and this is the big equation, okay? So we've got it written down here. Distance equals half acceleration times time squared, but we also have an additional piece, okay? It's going to be plus initial velocity times the time again. Okay, that's a lot of stuff. Let's get it piece by piece. Okay, distance traveled while braking. Let's get started. So, distance traveled while braking. We want to code it. Equal sign. All right, so in parentheses, I've got a half. Now, it's important you do 0.5 is a half. Okay, times the acceleration. So I've got it in this cell right here. And times the time of braking. And then this one is going to get squared. Now, how do I do a square? Well, I do Shift 6, which gives me a little up caret there. See, I've got an up caret. That's Shift 6, and then I do 2, and I put that all inside of the parentheses. Now, notice I don't have little multiplication signs in between, so let's do the multiplication signs in between. There we go. That's multiplying that stuff. Now, very carefully, look at our equation again. We have half times the acceleration times time squared, and then we have a plus sign right here, so let's put our plus sign in. Put the next term, okay, plus sign. Now I've got the initial velocity times the time. Initial velocity times time, so I'm going to put that right there. So initial velocity, in parentheses, I'm going to put my initial velocity 10, and then times the time again. There it is. Whew. All right, and then I'm going to hit enter. And now what we'd expected to see was 6.25, remember? But it's just rounding for us, so I'm going to do that decimal places trick again. Increase decimal places twice. Boop, boop. There's our 6.25 value that we expected to see from the systems analysis summary calculations. Okay, great. Now, we've got all of our values calculated. Now, we need to calculate the total distance the car travels. And hey, that's a calculation too. So let's code this as red. And the distance to Walker is actually an input. Okay, we can change how far away that Walker starts. And let's say the Walker starts away, I don't know, 50 meters. 50 meters. And then this distance traveled is going to be a distance, so we're going to have meters as well. And then right here, we need to calculate the total distance the car travels. Well, the total distance the car travels is just the distance traveled while distracted, plus the distance traveled while reacting, plus the distance traveled while braking, right? So see in the diagram here, this total distance over here, this total distance is all 3 of those distances added up. Whew, complicated problem, right? Okay, so we've got the total distance is just equal to this cell, and see how this cell came floating up with me just to show me that I'm still coding here. Okay, so I click on this one, scroll down, I have this cell, oops, excuse me. So I've got this cell plus this cell right here plus this cell right here, equal sign, gives me my total distance of 59.25 meters. Oh no, that looks pretty bad, right? Look, we traveled further than our initial distance to the Walker. Okay, well, how do we actually have the computer report what happened? Well, let's put this down here. this is going to be a new thing we're doing here, okay? This is a true-false statement, okay? So I'm going to do equal sign, because this is kind of like a bit of code. The true-false statement starts like this. If. It's an if statement, okay? So I put a parentheses here. So it says if, logical expression, value of true, value of false. Well, okay, let's take it step by step. If this distance here in cell E31 is greater than, so I've got a greater than sign. There's my alligator. The alligator wants to eat the thing that is bigger because it's very hungry, okay? The alligator wants to eat this distance. If the distance the car travels is greater than this distance right here, comma, then it's going to spit out a number, okay? So, or it's going to spit out a phrase if we want it to. So, if this is true, what happens to the pedestrian? If the distance traveled by the car is greater than the total distance of the walker, well, the pedestrian's in trouble, right? Okay, so we're going to put in a phrase here. So, it has to be in quotes if we want it to spit out some words, okay? So, I can put in the phrase, call 911. Okay, you can put in whatever phrase you want, all right? But I have call 911 because that walker is in trouble. Okay, that is if the value is true. See down there at the bottom, if it's true, it's going to spit out call 911. Now, comma, now this is what it's going to say if the value is false. So if this distance the car travels is less than the distance to the walker, you can put in quotes, you're safe, or something like that. Okay, and that's what's going to happen if the value is false. Now, when I hit enter here, it's going to spit out call 911. Because the walker is traveled too far. Okay, let's test it out. Let's make our walker safe again. Okay, how do we do that? Well, remember, guys, the whole point of this is to get you to think about whether or not we should text or drive. So if you're not texting, guess what your distracted time is? It's 0. Boom. Now, what's the distance traveled if you're not distracted? 0. You don't go that distance because you're not texting, okay? So you're immediately able to react. You travel 3 meters, and then you're immediately able to hit the brakes. 6.25 meters traveled. Oh, you're able to stop just in time. The pedestrian is safe. Hey, how about that? We figured out the solution to texting and driving using physics. Super cool. Okay, that is the texting and driving video for your simulator. Thank you very much, and enjoy your coding.